Over 4 centuries ago, Johannes Kepler derived his laws of planetary motion. Kepler's third law is equivalent to this equation, which finds the gravitational parameter of any given body from the velocity squared of any of its satellites times the radius of the satellite's orbit. Almost a century after Kepler's discoveries, Sir Isaac Newton theorized that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between their centers of mass. A modern interpretation of Newton's theory is that gravitational force results from a universal constant times the masses of two attracted bodies divided by the square of the distance between them. About a century after Newton's theory of universal gravitation, Charles Augustin de Coulomb first published his theory of electrostatic force. Throughout the centuries since then, many scientists have noted that Coulomb's law of electric force is remarkably similar to Newton's law of gravitational force. A few years after Coulomb's theory, Henry Cavendish made the first experimental measurement of Newton's gravitational constant. By rearranging Newton's equation to solve for the gravitational constant, Cavendish determined the value of g from the small force of attraction measured between metal spheres of known mass separated by a known distance. Despite nearly 2 centuries of progress in measurement technology, our modern value for g is only 1 digit more accurate than Cavendish's value. The measurement of all other physical constants has improved by orders of magnitude during that same time. The problem with the universal gravitational constant is that Newton's theory is wrong. A close examination of the so-called universal gravitational constant reveals that it equals the sun's gravitational parameter divided by the sun's Newtonian mass. That is nowhere near a proton's gravitational parameter divided by a proton's mass. Thus, the gravitational constant is not universal. Kepler's third law of planetary motion can determine either gravitational or electrostatic forces without using constants. In its simplest form, Kepler's third law reduces to the gravitational parameter for the body being orbited. That gravitational parameter quickly determines the force between two astronomical bodies or two subatomic particles, regardless of their electrostatic charges. It is easiest to determine the force acting on planets or subatomic particles from the potential energy of the satellite divided by the distance between the centers of mass. Because g is not universal, Planck units are a seriously flawed concept. More generally, it is necessary to reevaluate all equations that use Newton's gravitational constant. Thank you for watching this presentation.